Okay, so let me just pick up where I left off before. And we're going to start with another mode you can actually do XPS in, and that is imaging mode. So if you have an instrument that is so equipped, you can not only do high energy resolution spectroscopy like you saw earlier this morning, you can also, by having, in this case, a hybrid analyzer, where it's basically two analyzers in one, you can run the instrument in different modes. So in this case, we'll open up the aperture at the entrance plane of the analyzer. And so then in this mode, we'll transfer a two-dimensional image of your sample to the detection plane. And in this design, by putting the detection planes both in the same plane, and they're both real imaging plane, you could jump back and forth between spectra and imaging quite conveniently without needing to move your sample. Now here's an example of some microcontact printing that was done here at the university, where they wanted to confirm this step, that the platinum catalyst that was being used to etch the porous silicon pixels was actually selectively depositing inside these little circles. And so by doing two XPS images, carbon in blue and platinum in orange, we were able to see that the platinum was located inside the circles as desired. Then we could jump into, out of the imaging mode into the spectroscopy mode, collect some data within a dot. We could see fairly nice platinum signal within the dot, and then move off the dot and actually see quite a diminished signal. We are still picking up a little bit of platinum, so that could either be at the tail of the spot that we're analyzing, or we are getting small amounts of platinum depositing them up around the surface. Okay, so this is one example of XPS combined with ion sputtering that I'd like to show. This technique known as depth profiling. Tim went through this in quite a bit of detail, but you can actually do some depth profiling in XPS. In most cases, though, with XPS, because of the physical interactions of the ion beam with your material, there is quite a bit of chemical and electronic damage done to your material. Tim showed some really beautiful models of how that looks. And so in most cases, if you were to sputter a metal oxide, due to preferential removal of the oxygen, the metal reduces. So, but in this case, this group wanted to study the interface of the amorphous silicon carbide layer that's on top of the transparent tin oxide layer, look for any evidence of reduction at this interface. And section reduction would affect the transparency at the interface and affect the photovoltaics efficiency. So as I mentioned, in most cases the oxides are reduced, but tin oxide is one lucky case where the oxide does reduce, but it does not reduce fully to the metallic state. So I thought, I can probably do this experiment and get a result. So when we sputter from the surface down to this interface right here, you can actually see a little bump develop, indicating the presence of tin metal. So this does, in fact, show that there was a little bit of reduction at the interface that carried through. And to demonstrate further that the sputtering process was not inducing this reduction, we went deeper within the tin oxide layer, and we see that eventually that bump disappears as you get into just tin oxide. Here's another example in both XPS and UPS of the effects of ion sputtering. And so this is the first order transition metal nitride, titanium nitride, that I showed you earlier in the talk. Remember we had these satellites that indicate unscreened final states. And so after sputtering, and these are conditions typical for sputter cleaning, just a few minutes, we noticed that these satellites are diminished quite a bit. And that's because we were preferentially removing nitrogen. Nitrogen's reducing to a lower oxidation state. It's actually becoming more metallic, and we're providing more screening electrons to the titanium. So you see, just by a few minutes of sputtering, we altered the electronic structure of the material quite a bit. Here's another example of scandium nitride. Scandium nitride happens to be a wide bandgap semiconductor. which is evidenced by this diminishing density states up to the Fermi level. And so the black is before sputtering. After a few minutes of argon-ion sputtering, you'll notice in this red curve, we actually induced a little bit of a Fermi edge. So in this case, we're doping this material with charge carriers. And so again, changing the electronic structure of the material. This is one quick mention of another application you can use UPS for, and that is work function measurements. Like I mentioned earlier this morning, there's a lot of attention being drawn towards two-dimensional materials, graphene, hexagonal boron nitride, aluminum disulfide. And there's a lot of also interest in modifying the surface of graphene to actually either to induce a band gap. As you know, graphene is a zero band gap semiconductor. You can, by putting things selectively at the surface, you can actually make a band gap in various electronic properties. So this shows an example of how you measure a work function. The work function, as you know, is the difference between the Fermi level and the vacuum level. Okay, and so basically what we're looking for is the onset of electron emission. Okay, and then we can take the energy of the photon and look at the difference between that energy level and the Fermi level and deduce the work function. Okay, this is just a quick summary. XPS sensitivities in the tenths of atomic percent. Chemical information, yes for most. Depth resolutions in the nanometer range. Sample types can go solid UHV compatible, conducting, semiconducting, and insulating with modern spectrometers. UPS, not usually elemental analysis. Chemical state information, yes, but it's complicated because that usually requires modeling. Depth resolution is a little bit less than XPS. Lateral resolution, several microns, that's limited by the lamp. And sample type solid UHV, and mostly conducting or not very insulating semiconductors. Okay, let's now move into Auger Electron Spectroscopy. And then in this technique, traditionally we use an electron to excite the sample and analyze with an electron beam. I should probably look to see how long I have. Okay. Okay, just want to make sure I don't go over. So now Auger Electron Spectroscopy is a widely used technique for elemental analysis. It was first discovered in 1922 by Lisa Meitner, and then later independently discovered once again by Pierre Auger in 1925. And so the name actually stuck with him, Auger Electron Spectroscopy, which was most likely the result of some scientific sexism of the early 19th century. So, fortunately, Lisa was recognized in her own respect, and the element 109 was actually named after her, Meitnerium. Okay, this is a cartoon demonstrating the particle interaction with the solid that we see with Auger. So you'll see this diagram come up later in the afternoon. So you have the focused electron beam interacts with the sample. Different than a photon, the electron can transfer parts of its energy. It doesn't have to transfer its entire energy to an individual atom. It can incrementally transfer energy, in which case it can actually interact quite a bit with the sample. So depending on your energy, you can go down several microns, exciting particles in that whole volume. And as I mentioned earlier in this morning's talk, Auger Electron Spectroscopy being a technique that we're looking at electrons, it is very surface sensitive, and so we'll be just concentrating on these electrons here. And because we're very close to the surface in this area, we're close to the neck of the bottle. So it turns out our analysis area is pretty comparable to the probe dimensions. So we'll get roughly maybe half micron lateral resolutions. Here is once again a repeat of the physics. In this case, the electron comes in, excites a secondary electron, and then through a relaxation process, an upper shell electron falls to fill that hole, and then the third electron, the Auger electron, is emitted. And this is what we'll be looking at. just a reminder that the complementary process that takes place is the emission of an X-ray photon. And it so happens that the probability for, in this case, a K-shell relaxation is much higher for resulting in an Auger electron for the lighter elements than the heavier elements. Okay, so it's actually the complement of EDS. But the nice thing is then, this gives you access to the lighter elements. EDS gives you access to the heavier elements. And so it's nice to have both instruments in the same lab. One is a little bit better at the surface, Auger that is, and one's a little bit better in depth, EDS. Okay, here's a diagram of the Auger spectrometer that we have in the lab. First thing you'll notice that it looks a lot like an SEM. That's basically because that's what it is. It's an SEM with an energy analyzer surrounding the electron gun. And so the electrons are projected at the sample here, and they pass through this football-shaped pathway, and that filters the energies, and we'll collect them there. Okay, just a reminder that because the deep core levels and the upper core levels both shift to higher binding energy as you increase the atomic number, as well as the separation between the orbitals increase with atomic number, that's what allows us to identify the characteristic lines of all the different elements. And the same trend applies to Auger. The kinetic energies for the transitions increase with atomic number, as you would expect. And here I show two examples of Auger survey spectra for the first row transition metals, similar to the XPS data we showed earlier. The one thing you'll notice right away, though, is that the Auger transition is much more complicated in terms of number of lines and the energies they span as compared to the photoelectron lines. And that adds some complications to the spectroscopy in not only being able to identify elements, but also to be able to precisely do quantitative analysis. That's why it's also good to have an XPS system in the same lab as the Auger system. Traditionally, Auger spectra can be presented 2 different ways. The first way is the N of E mode, where you'll see that the lines are fairly small on a linear and intense background. And so in that case, we can also do a first derivative of the spectra. That way we enhance the signal quite a bit and give us a little bit more sensitivity to lower concentration elements. Okay, here's a couple of examples of Auger. And these lines are now, I'm comparing Auger signal that was produced by the electron beam. And if you remember my survey spectra at the beginning, we can also create Auger lines with an X-ray photon. And as you can see, the lines look about the same, which you'd expect because the physics is the same, only the exciting particle is different. Because of the design of our photoelectron spectrometer, well, you'll notice that we get a little bit better energy resolution with the X-ray induced Auger spectrum as compared to the Auger electron induced spectrum. That's because in order to make the Auger spectrometer of a coaxial design like we have, they have to make some sacrifices in terms of the energy resolution of the instrument. And in most cases, we use Auger for elemental analysis, but in many cases, we can get chemical selectivity. Here's an example of silicon carbide with highly ordered pyrolytic graphite. And besides the peak energy shift, I adjusted the kinetic energy scale of these lines just for comparison. I overlapped the two. So besides the energy shift of this line, there's a little bit of change in the shape of the pre-peak. And you use that then to differentiate HOPG from SIC. Again, this is a comparison of that same line. Same set of data collected with the X-ray source instead. A little bit extra detail you can see on the X-ray induced Auger spectra. Okay, I mentioned earlier this morning there's a trick I can play to extend the range of what we could look at with a conventional X-ray source. Okay, so this is how we produce the X-rays in our X-ray source. We actually use the same physics that you use to produce the X-ray photon that you use in EDS. So we'll use that as our X-ray source. So this is how our X-ray source emits characteristic X-rays. But if you use an X-ray source that does not have a monochromator, you can actually watch how that electron interacts. We'll understand that electron, as it is going into the anode, will interact with your anode material. And at any point in time, when the electron interacts with a proton and it changes direction, the momentum also changes, and then because momentum must be conserved, an X-ray photon is emitted. We call this X-ray Bremsstralung, or breaking radiation. And we can have these X-rays up to the energy of the electron beam. Now this will be a broadband X-ray, so we'd not be able to use this X-ray to do photoelectron spectroscopy, because we just get a random distribution of photoelectron lines. We can use it for Auger electrons generation, because those kinetic energies are only dependent upon the differences in the orbitals. So here's an example where I used an X-ray source to excite the KLL transition of silicon, which happens to be at 1600 EV. So that's already 230 EV higher than the source energy of the monochromatic X-ray source that we have. Again, we see that we do get some chemical selectivity with the Auger lines, just like XPS. I'm going to skip to here. Okay, and so like XPS, you'd like to be able to relate the signal to the quantity of species that are within the material. And you'll get an equation with Auger that's similar to the form of the equation we've seen for XPS, with the addition of two other parameters: the ionization or scattering cross-section for the incident electron, and the Auger transition probability, and the secondary ionization coefficient. But like I said earlier, because we calculate the percentages as a concentration, we can remove the instrument-dependent terms, lump all the rest of these terms into a relative sensitivity factor, and then use that for quantification. Now, Auger, because of its difficulties of overlap with other peaks, it's not quite as quantitative as XPS. It's going to be more on the semi-quantitative side. And its sensitivities span the same range, 3 orders of magnitude, as XPS. So the one thing you'll notice on this log scale is that they'll hit a peak, and then the sensitivity will sharply drop. Okay? That's because the Auger transition is a many-body process. You have to get 3 things to work out right for the transition to work. And so usually that only works for a small range of elements, and then you lose signal. But we can play with the electron beam energy, and so we go from 3 to 10 keV to enhance the sensitivity of some of these heavier elements. But all is not lost. Even though a lot of the elements have a low sensitivity, we can't see a lot of them. We do drop out when we get to the higher Z elements. And so if you get to something like gold, we may only be able to see maybe our limited detection will be in the several atomic % range. Okay, let's jump up to some other capabilities. Okay, so because the Auger behaves like an SEM, you can use it as an SEM. Okay, so here we have an SEM image of a sample, and they're interested in studying the etching of iridium from this pattern sample. Indium, indium. And so they're concerned at what the edges of the pads look like. So we located a little pad right here, increased the magnification, then switched over into Auger mode, collected an indium map, and we see that the etch process did not fully remove indium from the edges of the pad. And so that would be an example where these people would have to modify their etch process to correct that. Here's another example of combination of imaging with spectroscopy. And this is a pretty simple one. We see a lot of contrast here in this SEM image. We have a light area and a darker area. And because we can move the electron probe around, we can look at a section we'll call A, which is above, very nickel rich. The B, the darker area, very chromium rich. And so by now, we can collect a chromium and carbon map. I'll use this example. We say a lot of areas that are chromium rich here, and then areas where carbon rich are down here. And then by plotting the intensity of each of the pixels for carbon and chromium, we can look at where they correlate. And so we can now select an area here, and then an area here for the carbon, and then identify the various phases present in this material. And here's an example where we're going to combine spectroscopy, imaging, and depth profiling. So here, we're studying a carbon fiber in a boron nitride matrix. And a lot of the times in these composite materials, the properties of the composite relate to the interaction of the fiber with the matrix. And so sometimes the producers of these fibers will want to modify this surface to vary the properties or the interaction between the two. And so we can, first of all, collect an image, select the fiber we want to zoom in on, collect the spectrum, identify all the elements that we have present, then look at these elements as a function of depth as we sputter into them. And so here we can see we're combining a bunch of different methods with the same technique. So it's the same reason you'd actually use a bunch of different techniques for your analysis. Here's an example where you'd want to use a bunch of different methods of the same technique to enhance the amount of information you can extract from your material. And so that leaves me to just a quick summary. Auger, we're going to be able to see lithium and above. The one drawback of Auger is to make the Auger process work, you have to start with at least 3 electrons. And lithium happens to be the first element that we have 3 electrons. And so I want all you guys that can remember my Auger transition process, the physics behind the process, to try to figure out in your minds how we get an Auger electron out of lithium. It's not as easy as you think. Non-destructive, we will suffer some beam damage if you have electronegatives. Mostly elemental analysis, semi-quantitative. Chemical state of information from several elements, not for everything. It's not always as easy to extract as with XPS. Depth resolution comparable to XPS. Lateral resolution with our instrument is about half a micron. You can now go sub 10 nanometer with the field emission Auger systems. Sample type, once again, just like XPS, UHV compatible. We can work with conducting, semiconducting for very insulating samples. We may have some limitations. You may have to coat your sample. And with that, I'd like to conclude and once again thank our sponsors.